So in the last two lectures, we've spent time developing the basics of mathematical logic. But now we need to think of it a little bit more as a general language. And just as when you learned algebra, there were lots of rules that you kind of needed to learn about how you combine things algebraically, we need to do that for logic. So let's start by having a look at more general compound statements. So these are statements that contain many atomic propositions. And we'd like to find the truth table for something like this. So here we have P or Q and not P and Q. And we'd like to know for what values of P and Q is this true and false. So the trick to solving these kinds of things is to work step by step. So we're going to build up a truth table, but it's going to have a lot more columns than we're used to. So we're going to start out with the standard truth table for P and Q. In the usual order, we want to know when both of them are false, when P is false and Q is true, when P is true and Q is false, and when they're both true. And now we start breaking up our long statement into smaller bits. So let's work out P or Q. Well, we know that P or Q is true most of the time. The only time it's not true is when both P and Q are false. So remember, this is OR. And we're also going to need P and Q. And this is only true when both P and Q are true. The rest of the time, it's false. But in fact, in this sentence, we're going to need not P or Q. So remember, negation just changes everything that's true to false and false to true. So not P and Q is going to be true for every case except when both P and Q are not true. So now we get to combine our P or Q. So we've got our P or Q, which is this column over here, and our not P and Q, which is this column over here. And finally, we can work out the truth table that we actually want. So notice we need to combine our P or Q column and our not P and Q column with an and. So we're using whatever we find in this column and whatever we find in this column and making the appropriate choice. So if we start when P or Q is false and not P and Q is true, then we have false and true, which when we join with and, we know is false. When we have both are true, then our statement and other statement is true. In our third line, we have true and true, so combining with and, we get true. And then in our final line, P or Q is true, but not P and Q is false, so combining them with and, we get false. So now we know that for values of P false and Q false, our general compound statement here is 0, is false. If one of them is true and one of them is false, then our compound statement is true. And if they're both true, then our compound statement is false. Okay, so take a moment to just work through this and make sure that you understand how we did it. You'll find it takes a little while and then it becomes second nature, just like working through algebra. So now we can start to ask questions like the following. Is the statement not P and Q the same as not P and not Q? So just a reminder, sometimes we can use this little tilde instead of not. So we haven't actually defined what it means for two logical statements to be the same or equivalent. For the moment, let's just say that they have the same truth values. So their truth tables look the same for if you have the same P and the Q. All right, well, let's put together a truth table for each of them. So we've got our P and Q in our standard truth table. So we've got a 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. And let's go ahead and figure out. So I'm going to start by just writing down P and Q, which we know is false unless both P and Q are true. And then we actually need to have not P and Q. So we have not P and Q. So that's the negation of P and Q. And we want to compare that. Well, here I need not P and not Q. So not P is going to be 1, 1, 0, 0. Not Q is 1, 0, 1, 0. So I've just negated both those columns. And now I want to combine those into not P and not Q. So here I'm using these two columns and combining them with and. So I've got not P. If not P is 1 and not Q is 1, then combining them with and will be true. In all the other cases, we know that and, unless both things are true, and will be false, so and is going to be false. So finally we can answer the question, which was asking us, is this statement equivalent to this statement? And as you can see, since they have quite different truth values depending on P and Q, we can conclude that they are not, in fact, equivalent. So this is quite an important thing to realize, because if you think in sort of algebraic terms, you might have thought that if you have a not outside a bracket, that you could just distribute it in, which is really what we did over here, but it turns out clearly you can't. So we can't distribute not. Let's see if this makes sense. So we're wanting to think about what it means if we negate ands and ors. So take a moment to negate the following statements. The earth is round and the sea is wet. So if we start breaking this up, we've got the earth is round, so that's one atomic statement, and the sea is wet, that's another atomic proposition, and we're linking them with and. So if we negate this, we're going to have the earth is not round. I'm leaving a space over here for whether it should be and or, and the sea is not wet. So we want this sentence to mean not the case that the earth is round and the sea is wet. So if we want it to be not that the earth is round and the sea is wet, it means that one of them needs to not be round, or rather one of them needs to not be true. So we need to have that the earth is not round or the sea is not wet, because that will give us the negation. If we look at the second sentence, I will go to the shops today or tomorrow, if we want the negation of that, we're going to have I will not go to the shops today and tomorrow. And if we look at the more mathematical one, if we want the opposite of x is less than 2, then our opposite will be, our negation will be x is greater than or equal to 2. So these ideas lead us to De Morgan's laws, which really teach us about distributing not over ands and ors. So one thing you might notice is this funny little 3 lines equalish looking thing. This is equivalence or equivalent, and it works just like equals does in algebra, but we use equivalent or equivalence in logic, and we will define it a little bit later. So we'll define it later. For the moment, think of it like equals. We need a couple more definitions before we can actually define it officially. So De Morgan's laws say if you want to negate P and Q, then what you actually have is not P or not Q. On the other hand, if you want to negate P or Q, that is the same as saying not P and not Q. As an exercise, you should just check that these truth tables are the same. So as your exercise, check truth tables. So do a truth table for this and a truth table for this and check that they're the same. Then a truth table for this and a truth table for this and check that those two are the same. And I will put these in the final notes so you can double check. Okay, so we've learned how to distribute not over and and or, but as we saw in the very first example, logical statements can become quite convoluted. So just as you had to learn BODMAS, if you remember, for algebra, where this teaches you that you need to put brackets first and what else, and the ordering that you pass an algebraic sentence, we need to have similar rules for logical operators. So here's how we order things. So the very first thing that you do if you've got a sentence in logic is first negation. Okay, so if you see a not or a tilde, deal with that first. Then the second thing that you're going to look at is conjunction. So remember, this is our and. And then the third thing that you'll look at is disjunction, which remember is or. Conditional, so remember that's the one-way arrow. And finally, if you've got any double arrows, you'll work that one last. Within any level of the hierarchy, you work from left to right. So for example, if you were just given this, it would take to mean P and Q, you do that first, or R. And these rules are universal, and they're used by computer languages to interpret logical expressions. So when your computer's doing logic, this is how it's thinking about it. So let's just use parentheses to show the correct order of calculation of the following. So we've got P and Q and R. Well, we don't have any negation, and then we just have conjunction, so we need to work from left to right. So we can say this is equivalent to first computing P and Q, and then and R. Now if we have a look at the second one, we've got nots coming in, so those have to happen first. So we have, you work not P and not Q, and then you combine them with your disjunction, or. And if we look at this next one, now we have not P. Well, deal with negation first. So we're going to negate P first, and now we work left to right. So we have not P. And as you would imagine, this will come out as just P if you were to check the truth table. So we have two cases that get special names. So tautologies in logic are a little bit different from the tautologies you learned in English. A tautology is an expression involving logical variables that is always true. So these are things where if you draw up the truth table, then your final column is all ones. So let's pick one of these as an example, and you can work through the rest and check that they are. So how about this very simple one? So we want to check that this is a tautology. It's saying P or not P. So if we draw up our truth table, well, this only has P's, so we just need a 0 and a 1. And then we need not P, which is going to be 1, 0. And if we combine these with OR, well, if P is false and not P is true, combining them with OR is going to be true. And if we combine a 1 and a 0 with OR, that's going to give us true as well. So this is a tautology. You can think about it as saying the dog is brown or the dog is not brown. Well, that's always going to be true. If it's a dog, it will be brown or it will not be brown. Now let's look at a slightly more interesting example. So let's have a look at this one. So we want to check that Q implies P or Q is true. All right, and we want to see that that's a tautology. So we're going to need a truth table with P and Q. So we've got 0, 0, 1, 1, 0, 1, 1. And we're going to need P or Q. And that's false when they're both false but otherwise true. And now we want to think about the truth value of Q implies P or Q. So we want Q implies P or Q. So think back to our truth table for if Q then conclusion. Go back and check if you want to revise it. So what we're saying here is we've got if Q is true, then P or Q true. That's really what we're asking. Is this always going to be the case? Well, if we think about our implication, we said that if our condition was false and the conclusion was false, then we couldn't really say anything about the statement if Q then P or Q because the condition wasn't met. So our statement was true. If both the condition and the conclusion are true, then the statement is true. If the condition isn't met, but the conclusion is met, the statement is still true. And finally, we have the same line again. If condition and conclusion are both met, then the statement is true. So here we have a tautology. So again, as an exercise, just work through the three remaining ones and check that those are all tautologies. It's good practice for getting used to your logic tables. In contrast to a tautology, we have the idea of a contradiction, which is something that is false for all cases. And we often use the number 0 to symbolize a contradiction. So, for example, we could have a look at P and not P and check that that's a contradiction. Let's do that quickly. So we've got P, which is either 0 or 1, not P, which is 1, 0. And then if we combine them, so we've got P and not P, well, they both have to be true for this to be true, and there's no case in which they are. So it's false. So this is a contradiction. So you should take some time to just sketch up the truth table for this and check that your final column is a row of all zeros. So now we're actually in a position to define equivalence, which we've been using by thinking of things having the same final truth table row, final truth table column. But we can actually define it formally. So if we have two propositions, proposition R and S, then they're equivalent if the truth table for R is true if and only if S is true is a tautology. So if we put together, so if we take our propositions R and S, whatever they might be, and we check the if and only if table, if that table ends up with ones all down the final column, then we've got a tautology. And we have quite a bunch of different notation. So we've been using 3 lines for equivalence, but sometimes you'll also see single and double-headed arrows being used. So don't be confused. This can feel a little bit weird because we've already thought of this as meaning if and only if, but the whole point is that we're using if and only if to define equivalence, and that's why it kind of gets used for the same thing. But whenever we're talking about equivalence, what you really want to think of is equality in algebra. So it's worthwhile working through this list of basic laws, which are similar in many ways to the basic laws of algebra that you don't even really think about using anymore. So you remember commutativity from algebra, which said, for example, a plus b is equal to b plus a. And what we have over here is that you can say P or Q, or you can say Q or P. It doesn't matter which order you put them in. And the same goes for ordering and. So P and Q is exactly the same as saying Q and P. We have associative laws. So if you remember from multiplication, you have A times B times C is the same as saying A times B first and then C. And this is saying if you've got a whole string of ors, or you have a whole string of ands, then ordering doesn't really matter. So we do have the rules that we learned earlier which say how you should go about doing the ordering, but it doesn't matter. We have some distributive laws. So now we're talking about combining ands and ors. If you think about the distributive laws, this tells us how to deal with things like A times B plus C, and you know that you can distribute the A in if we're talking about multiplication and addition. And it turns out that the rules that you use are pretty similar. So if we've got P and then we've got Q or R, that's the same as P and Q or P and R. And going the other way around, we've got P or Q and R, again, distributes. So it looks a lot like the distributive laws for addition. But remember, this doesn't work for negation. For negation, you're going to need De Morgan's laws. A couple of identity laws. Well, if you've got P or 0, so P or false, then that's exactly the same as just saying P. And in some ways, this is a little bit like saying 32 plus 0 is just equal to 32. So 0 kind of acts like, so false in this case, acts like 0 in addition. When you're dealing with an or, on the other hand, when you've got an and, 1 kind of acts, or true, acts like 1 in multiplication. So you'll see that this is kind of building up an idea that OR is sort of a bit like addition, whereas AND acts a little bit like multiplication. If we think about combining something and its negative, if we have P and not P, well, that can't ever be true. So that's always 0. On the other hand, P or not P, well then something's always going to be true. So that's true there. And there are a few more rules that you can have a look through and check that their truth tables are right. Here are De Morgan's laws, which tell us how to deal with negation. And finally, we've seen this before, but just to clarify, not P is the same as P. So if you're wanting practice with truth tables, you can just check that all of these make sense. So here we have a table of equivalences and implications. So just to remind you, equivalences are statements that really have the same logical table, and implications are one thing implies another. You don't have to learn these off by heart, but it's a good idea to go through them and see that they make sense. So you do that by just checking the truth table. So in particular, it's worth noting that one way that you can simplify a conditional statement, so an if P then Q, is into not P or Q. So just to give ourselves a little bit of practice, let's check that these are equivalent. So we've got our P and our Q. Okay, so we know that P implies Q is true for every case except where the condition is true and the conclusion is false. Now let's have a look at not P. So not P is going to be 1, 1, 0, 0. And we want not P or Q. So to work out not P or Q, we're using not P and our Q column. And remember, if we've got an OR, we could rewrite this. It's the same as saying Q or not P. So we can use this as our first column and this as our second column. And we're combining with an OR. If Q is false and not P is true, then this is going to be true because it's one or the other. If they're both true, then it's true. If they're both false, then OR is false. And if one of them is true, then it's true. So finally we can check this equivalence over here. Are these two things equivalent? We're wanting to check that this column is the same as this column, and yes, they are. So those are equivalent. The other statement that it's useful, the other equivalence that's useful is the biconditional equivalence. This looks like a long thing, so let's just check what we've got here. Well, what we've got is that P if and only if Q could be rewritten as P implies Q and Q implies P, because that's how we defined it. But then what we do is we use our conditional equivalence from up above to be able to take this biconditional equivalence and turn it into something that only involves ands and ors. And then the final useful thing to have a look at is our contrapositive, which we've seen before. And this says you can turn if P then Q into not Q then not P. So spend some time just working through these and checking that you're happy with the implications and equivalences.